So today we are talking about energy changes. As in some books you will see there what you call chemical energetics or thermochemistry. But what matters to know that we are going to deal with energy. Remember, the main source of energy is the sun, but we keep on transforming it from one form to another. Now, majorly what we are going to look at under this topic is what we call heat change or enthalpy change. Now, before I define enthalpy change, I want you to drive you backwards. You always know that if you are using charcoal at home, you produce some heat which makes the water to boil, the food to become ready. When you put petrol in a car, when you put diesel, when you put paraffin in the candle, you discover the energy is produced. So when you eat food and food is broken down, you get energy. So that kind of chemistry is what you want to look at under this energy change. So to understand energy changes properly, we have to talk about what we call enthalpy. Enthalpy is something simple, just meaning the heat content. This one simply means the heat content contained in 1 mole of a substance. Contained in 1 mole of a substance. That is the enthalpy. So this implies that substances contain bonds. So when you break bonds or when you form bonds, you end up either absorbing heat, energy, or losing heat energy. Now, after understanding the definition of enthalpy, that is the heat content of a substance, then we can look at what we call types of reactions. Now, basing on enthalpy changes which occur. Basing on the enthalpy we have talked about, the heat content, we have 2 types of reactions. One of the reaction, we have what we call an exothermic reaction. And then what we call endothermic reaction. A reaction can only be exothermic if it produces heat outside. So we can say that this is a reaction, this is a reaction, this is a reaction that produces heat to the surrounding. How will you discover this one? For example, when you are using firewood at home or charcoal, you'll feel that even you around, the environment is becoming hot. So that as the environment is becoming hot, it means burning of carbon, which is in the charcoal and firewood, is releasing heat outside. So there we shall say the reaction is what? Exothermic. So this means that the heat of the environment increases. Heat of the surrounding increases. And how do we know a reaction? We can only discover the reaction is exothermic by feeling now that the environment near that reaction is becoming warm or hot and hot and hot. Reactions which are exothermic, we always represent them with a negative value. If, for example, if you are releasing, for example, 200 joules of heat, or kilojoules of heat, we put a negative. This is not a mathematical negative, but we are just denoting that you are giving heat outside. Alternatively, when you come to endothermic reactions, these ones are the opposite of these ones. Endothermic reactions, these are reactions. What is the reaction? The reaction that absorb heat from the surrounding. Now. So in this case, the surrounding environment is becoming cold. The heat energy is entering the reaction. So you discover that you are carrying out a reaction, but the outside surface of the container or the vessel you are using is becoming cold, but the inside part is becoming warm and warm. That one implies that now heat is absorbed. That is to say, heat is absorbed. It is entering inside the reaction. So this one, as we are denoting this one with a negative, for this one we are denoting it with a positive. So we have a positive there, as we are denoting the other one with a negative. This one we are denoting it with a positive value, indicating it is absorbing heat. Now, after understanding the two types of reactions, their meanings, we can go to the types of enthalpy changes. We have a number of enthalpy changes. We have enthalpy of combustion, enthalpy of solution, enthalpy of neutralization, enthalpy of displacement, and many others. But our area of concern first will be on what we call the enthalpy of combustion, or the heat of combustion. If you don't use the word enthalpy, you can use heat of. It's the same as heat now. Heat of something. Heat of something. That is the same as what? Enthalpy. So when I come to enthalpy of combustion, remember combustion means a reaction between the substance and oxygen. When you are burning a substance completely in oxygen, that is combustion. So when you add there the word enthalpy, that is when you are going to talk about the heat produced from what? Combustion. So to simplify the definition of enthalpy of combustion, this one is always asked. We can say that this is the amount. This is the amount of heat produced when one mole of a substance is completely burnt. Can be burned, or it can be burnt in excess what? In excess oxygen. This oxygen. Take an example when you burn carbon. You have carbon plus oxygen and you form carbon dioxide. Here now we are seeing that there is some heat given off. But if you are burning one mole, there we are going to talk about enthalpy of combustion. So if you don't call it now enthalpy of combustion, you can call it molar heat of combustion. Molar means one mole. Molar of a substance. Now in some cases the question may say, what is standard enthalpy? Standard enthalpy of combustion. Once they talk about standard, it means you are going to introduce in, you define and then you put there at standard conditions. That is if the question is adding the word standard. So if I come and say, well, define standard enthalpy of combustion, you will say that is the amount of heat produced when one mole of a substance is completely burnt in excess oxygen at standard what? Conditions. So from there, we come to an example. For example, they are saying here, how much heat is produced when 20 grams of carbon were burnt in oxygen. And they are telling us that the molar heat of combustion is that. When we are calculating that, when they say molar heat, it means this one is produced by one mole. So we have negative 393. We are saying kilojoules per mole. These ones are produced by one mole. But remember, one mole of a substance is equivalent to its R, relative atomic mass, or its RMM. And for the case of carbon is a relative atomic mass of 12 what? 12 grams. So what we are going to come and say here, we shall come and say that the 12 grams of carbon produces the 393 kilojoules per mole. Per mole. Then if the 12 grams of carbon produces this heat, the one they have given us in the question, what about those ones which we have in the question, the 20? What about the 20 grams of carbon? 2 grams of carbon. In this case, they are going to produce what? We are going to cross what? Cross multiply. When we are cross multiplying, we are going to discover that we have our 20 now times the 393 out of 12. So then try to place your calculators. I'm also placing here and we see what we are getting. So when you look at that, so we are going to obtain what we are calling 605 kilojoules. And now that will be the amount of heat which you have produced now by the 20 what? By the 20 grams. They always ask you these questions in the question what? In the question bank. So what matters is to understand this one. You can even calculate it backwards, assuming they have told you molar heat of combustion, this one, when you don't know it. But when they have told you that the 20 grams are producing that, you just reverse it. You just come and say 20 grams produces the 6.5 if it is given your joules. Then what about the 12 grams produce what? Then you are going to calculate it backwards, like that, out of 20. But what is the change here? The answer now is going to become in kilojoules per what? Per mole. The answer will come back to this one. When you take it back, you get 393 kilojoules per what? Per mole. Members, the negative here, you don't carry it. This one is just denoting. So this explains why I'm not using a negative here. So don't put it there. Now when we leave that, now we are going to move to a step ahead. That is an experiment to determine the type of combustion. When they always tell you to talk about experiment, you don't waste a lot of time outlining requirements, but you can just come to the procedure. Our procedure here, what are we going to do? Now to get the procedure properly, let me first make a simple illustration here. When you are going to carry out this experiment, you'll get just a tin which is thick-walled, like that. Our tin which is thick-walled. Then you are going to put a known volume of water there, as we are going to see, known volume of water. Then of course this tin, you have to hold it properly using a retort stand. You have to keep it firm like that. Then from there you have to get what you call a burner. We always call it a spirit burner. A burner is like a candle, but where you can put something to burn. Then you have to put what you call a wick. A wick. Then inside it you put what you want, the substance whose ether of combustion is needed. So we have our retort stand here. Then of course here you are going to reserving a base there, and then you are going to put a thermometer here to record the temperature changes. Have a thermometer there. So the setup in simple terms is going to be like what? Like that. But remember now, you have put the candle with the wick and you are going to light it. So the setup is going to be like that. But when you are drawing, you always try to draw a working apparatus. Apparatus which is clearly drawn. Don't just draw to do what? To complete. Now, from there, we are saying this is our beaker, which can be now a glass beaker, or it can be tin. Then you can even put an insulator here to insulate the heat. But since you have used the thick wall, this one is a thick walled tin. So this one, I'm saying it can even be a tin. So even it's thick walled, even if you don't use the insulator, but you can put an insulator here. Then we have our thermometer here. Thermometer. Then you have our burner. This is spirit burner. Then inside you have what you are going to burn. It can be substance like ethanol or propanol, anything. Then this one, of course, it is a flame. You are going to light it, and it's going to give off a flame. And here you have water. Inside you have water. You have water there. And this is our retort what? Retort stand. Like that. Now after setting up like that, so we can now convert this setup into procedure. So what are we going to do? We are going now to obtain to members. We are saying that after setting up like that, remember here you have to even put a cork. Then we want to transfer this one into words. So we are saying put a known volume of now water where in a thick walled beaker or tin. And secondly, we put a known mass, or it can even be volume, known mass of a substance whose What is the heat of combustion? Heat of combustion. Combustion is investigated. What is the heat of combustion is investigated in what? In a burner. A burner. Then secondly, we weigh the burner. Weigh the burner plus the substance. The substance using a weighing scale. Using a weighing scale. Then from there, what happens next? We take a note. Take a note of initial temperature. The temperature of water. The temperature of water using a thermometer. Using a thermometer. Then from there, we light the wick of the burner. So we reach the burner, then we leave the setup for some time. To raise temperature of the water. Then from there we record the temperature rise of the what? Of the water. Temperature rise of the water still. Now, after doing all of that one, we shall end up the weighing the burner plus the remaining substance. And from there now, we have to obtain our results, which we are going to do what we call. Then from there we go to what we call treatment of the results. Now our results, we are going to assume that we have the following results. Those are going to act as our sample results. We have in what we call, let us assume that the initial temperature of the water, it can be, for example, you can take a 24 degrees centigrade. Then you can take also final temperature of water, which you read as at the end of the experiment. That is final temperature of the water. Let us assume that the final temperature of the water is 40 degrees centigrade. Then we look at volume of water which we used. Remember, we measured it using a measuring cylinder. Don't forget to specify it in your procedure. Measuring it using a measuring cylinder. Let us assume that it is 100 cc or cubic centimeters. Then we have now the mass. Remember, we weighed the burner, mass of the burner plus the substance. Let me assume I'm using a substance known as ethanol. So I'm going to use ethanol to simplify the work. Ethanol. So I'm going to assume that one is going to be 32 grams. About 32 grams. Then we have mass of the burner still. Mass of the burner plus ethanol, which is our substance. At the end of the experiment now, this one at start. Then now we have at the end of our experiment. Let us assume that they are reduced to 30 grams. We are going to find the heat which was gained. Remember, as you are burning here, the water will become warm. And as the water is becoming warm, the temperature of the thermometer is going to raise than what it was before the experiment. Now when we are calculating, we are going to find the heat which the water absorbed. Even if you are cooking at home, you are putting firewood down, the water in the saucepan must boil on the kettle because the kettle is absorbing energy. So we have the water in our tin here. Take it to be like a saucepan or kettle. Now our heat absorbed by water will be exactly equal to the heat produced by the burning substance. But how are we going to get it? We are going to say this one is equivalent from principles of physics to mass times the specific heat capacity times the change in temperature, which physics always represented by eta. So this implies what? That we are going to find specific heat what? Specific heat capacity. Specific heat capacity is always known. Specific capacity is always known. It can be 4.2. Then our Q or theta is we are going to find it. How are we finding it? We are going to get now the final temperature. That is our final temperature, which is 40. Final temperature minus the initial temperature. Initial temperature. And now this implies that we have here our original, which is 40 degrees minus the 24. And here our DT is going to become 16 degrees. So we have our 16 degrees centigrade. So we have got the DT. Then the next step, we have to find mass. Because when you look at this formula, we have mass. How are we going to get mass? Mass, we are going to get it using the volume you have. The volume is there. We are going to use the formula saying mass is equal to density times volume. Then our density here, we are going to use the density of water, which is 1 gram per cubic centimeters. So we are going to get here now our density, which is 1 times our volume. Our volume is 100 times our density of 1. So we have grams which are equivalent to what? To 100. That is our mass. So members, we have got the mass of our water. So we are going to find heat. We are saying heat is equivalent to the mass, which mass is 100 times specific heat capacity, which we have got as 4.2 here. 4.2, there have been kilojoules. Then times our change in temperature, which was, you remember it was 16. Now, overall value, when we wrap up everything, now we are going to end up absorbing now 6720 kilojoules of heat. That is the heat which was absorbed by the water. But all of this heat which you have calculated is not produced by 1 mole. But the question is saying you have to find for 1 mole, that is the enthalpy of combustion. So what do? We have to calculate the moles of the substance which was burnt by using its mass. So how are we going to get the mass of burnt ethanol? Mass of burnt ethanol is going to be equivalent to the original mass which we talked about here when we are giving our results. Mass of the burner plus the ethanol was 32, that is before burning, then minus the mass of the burner and ethanol after burning, that was 30. And here we are going to obtain what we call 2 grams. How am I getting it? I've got the mass of the burner and ethanol before burning, then minus the mass of the burner and ethanol after burning, and I get now the 2 grams. After getting the 2 grams, these are the grams now which were burned. So what am I going to do here? I'm just going to come and say that, remember, I have to find the moles of ethanol by first finding the RFM of ethanol. So I'll just come and say, let me just simplify that moles are equivalent to mass of a substance over RFM. You can even use the first principles. So let me find RFM of ethanol. RFM of ethanol, our ethanol is like that. This is our ethanol. So we shall get now that is 12 times 2, because carbon is appearing 2 times. So that is 12 times 2. Then plus hydrogen is appearing how many times? 3, 5, 6. That is 1 times 6. Then plus 16 times 1. Oxygen is appearing once. And we end up getting 46. That is now our RFM. So we shall just come and say moles. Moles are just equivalent to the mass, which is 2 grams out of 46. and we are going to end up, place your calculator there and also see, mine is saying 0.044444 moles. These are our moles now. Now these are the moles which produce all of this energy, which you have got here. So we shall just come and say 0.044 produced the energy which was 6720 kilojoules. Then what about 1 mole? About 1 mole produces what? 1 mole produces what? And we get 1 times 6720 out of 0.044. And now our final answer here is going to become, becoming 15227 joules. You can convert them to kilojoules by dividing by 1,000. So if you want kilojoules, divide by 1,000, and it's giving us 152.7 kilojoules per what? Per mole now. That is per mole. Now, if this one is hard for you, you can also pass via the other direct method of first principle. And we can just get all of the grams which I have computed there. Or let me simplify by saying, you get the 46, you just come and say, the 2 grams of ethanol produces the heat which we got, that is the 6. This is another approach. This is the 6720. Then what about the 46 grams of ethanol produces? Then we cross multiply. We shall get 46 times the heat, our heat, that is 6720 out of what? Out of our 2. When you compute the answer, will still come back the other one which we have what? Got of the 152.727 joules per what? Joules per mole. That is our approach there. So you can get many questions which you are familiar to from the question what? From the question bank. Now from there, we are going to look at what we call the enthalpy of neutralization on a mole of water. So that heat which is produced becomes the heat of neutralization. If it is molar, you have catered for 1 mole. So what are we going to say here? We are going to say this is the heat, this is the amount of heat produced when 1 mole of an acid is reacted with 1 mole. Yeah. So members, we are saying enthalpy of neutralization is simply amount of heat produced when 1 mole of an acid is reacted with 1 mole of a base to produce 1 mole of water. Take an example. If you have the hydrogen ions, those are from the acid, plus the hydroxyl ions, those ones are from the alkali or the base. You are going to form water here as 1 mole. So you have 1 mole, 1 mole, 1 mole. So the heat produced here, it can even be negative enthalpy. That one is going to be what you call the heat of neutralization. Now we go to the experiment for carrying out this one. When you are looking at this experiment, you find that we shall get our beaker, which is also thick-walled, like that. Then we get our base, whose temperature has been noted using a thermometer. Then we add there our acid, whose temperature has been taken by thermometer still. So we have our thermometer here, which is going to help us to take our recordings there. Then we stir continuously. We are going to stir continuously using a thermometer. So we have our thick-walled beaker here, thick-walled beaker or tin. So we have our mixture here. This is a mixture of, for example, sodium hydroxide and maybe hydrochloric acid. You can use another acid. Then we have our thermometer here for stirring and recording temperature changes. So the simple setup can be like that. So, in simple terms here, if we are going to write our procedure, we can simplify the work by saying, we can say that the base or the known volume of a base is put in a beaker, and its initial temperature, its temperature is noted or recorded using thermometer. Recording using our thermometer. By doing that, then a known volume of an acid is put in a beaker, still another beaker, and the temperature and its initial temperature is noted. Is mixed with the base now, and the mixture is what? The mixture is stirred. The mixture is stirred continuously. So we are stirring our mixture. So we stir the mixture continuously here. Stir the mixture using a thermometer. Then temperature rise is noted. And from there, we are going to assume that these are our results. Take an example, we have used the hydrochloric acid. These are results. So we have our results here. In our results, we have volume of the acid now. Osmolarity is known, it can be 1 molar HCl. We can assume that is 50 cubic centimeters. Then volume of still 1 molar sodium hydroxide, that is our base. It can be 50 cubic centimeters still. Then secondly, we have what? Temperature of HCl, the initial temperature of HCl. You can say the temperature was 24 degrees. We are just assuming. Then temperature, look also temperature of sodium hydroxide. So I'm shortening these words, but you always write them when they are full. My space is not enough here. Then I may assume that this one is, let me give it 25 degrees centigrade. Then now, temperature of the mixture, which you have recorded lastly. So temperature of the mixture. Let us assume the temperature of the mixture, that is the temperature rise, is 30.83 degrees centigrade. Now from there, we are going to find the heat produced. So our calculation, which we are calling treatment of the results. Here we want to do what? To calculate. So first of all, I'm going to get the heat produced, but I'm going to use the same idea of mass times specific heat capacity times change in temperature, which we use like any type of combustion. So here what we are going to do, we are going to find mass of the solution. Mass of the solution, we are going to use the same, we shall say, is equivalent to density times what? Volume. So volume, where are we going to get it? We shall find total volume. Total volume, we shall add the 50 plus the 50, that is 100. So we shall get here density, which is 1 gram per cubic centimeter for water, then times the total volume. Our total volume, that is 50 plus our 50. Don't forget it. 50 of the base, 50 of the acid. And here 100 grams. 100 grams. Then after getting our 100 grams, then here we are going to substitute. Substituting, do we have a change in temperature, or the dt, or the theta? That one we are going to get now. The average temperature, remember we have the average temperature. We shall get the temperature of the mixture, temperature of a mixture minus average initial temperature. Let me call it average initial temperature. So we shall just come and say 30, that is the temperature of the mixture, then minus the average initial, which is 24, plus 25, divided by 2. And our average initial temperature, members, we are saying here, we are going to find our DT, and our DT we have agreed that we get the temperature of the mixture. Remember, temperature of the mixture was 30.83, that is the temperature rise. Then minus the average temperature. Average temperature, we are getting the temperature of the acid. Remember that, initial plus the temperature of the base, initial, then divided by 2. The 24 and then the 20 what? The 25. Then meaning we shall get our expression as it is there. We have our 30.83 minus the average of this. So we are going to put here minus the average. Our average is going to be 24.5. That is after adding the 2 divided by 2. Then we are arriving to our final answer as 6.33 degrees what? Centigrade. Remember, we are looking for molar heat of neutralization. So what we are going to do next, now we are going to, remember the formula we used, we said it is mass times specific heat capacity times change in heat, or change in temperature, which we have already got here as our DT. So our mass, we got it, our mass was 100 grams. Then what next? We are going to substitute. So we have our heat produced is now equivalent to the 100 times the 4.2, then times the 6.33. So then when we multiply our values like that, now we are going to end up having 2, when you get your calculator, 658.6 joules, which can also be 2.66 kilojoules. That is after dividing by 1,000. This value, you will get that one here. That is the heat produced by the whole solution now. But remember, we want the heat produced by 1 mole. But 1 mole, we are going to base on the moles of what? Moles of the water. So what are we going to do here? Now we are going to find the exact moles which are producing this amount of energy. How are we going to find the moles? We are going to go back to the volumes which they gave us and the molarity which they gave us. We can pick one of them and then we continue with it. So let us take this one for sodium hydroxide, for example. We are going to say now that 1,000, we are looking for moles now which produce this heat. 1,000 cubic centimeter contain 1 mole of sodium hydroxide. Then if the 1,000 is containing that, what about the 50 here? What about the 50 cubic centimeters of the same solution contain? We are going to cross multiply. That is 50 times 1 out of 1,000. Those are moles. And now our moles which we are going to get there, they are 0.05 moles. These moles, even if we take the other root of the acid, we shall get the same moles. This explains why I'm taking only 1, because they are the same. Now from there, that implies those are the moles which are producing this heat. So here we are going to say, therefore, the 0.05 moles of now the base, if you have used the acid, you say, of the acid, that is of sodium hydroxide, produces this heat which you have calculated. That is the 2.66. Don't forget that. The 2.66 kilojoules. And what about 1 mole? Since we are looking for molar enthalpy, 1 mole of sodium hydroxide produces, then we are going to cross multiply. So we are going to get our resultant value here. We're going to get now the 1 times the 2.66 over the 0.05. Then the value we are going to obtain here is going to become 5, 3, when you get your calculator, 0.2. Now, and this one is going to become now our heat produced by 1 mole. Therefore, if you say kilojoules, the kilojoules are going to be per watt per mole, like that. Now, the figure we have obtained here, that is not accurate. We may have some errors there in the values you obtain. The experiment, however, is going to be approximate what you want. So now the other enthalpy we are going to look at, the third one, that is enthalpy of displacement. So we're going to look at what we call enthalpy of displacement. Enthalpy of displacement. Now, this one is arising from the definition of displacement. That is where a more electropositive element replaces now a less electropositive what? Element. And in the due course, take an example. If you have, for instance, copper sulfate, and then you react it with the zinc, we see that the zinc is higher in activity steady, so the zinc is going to replace the copper. So to find here, we shall get copper solid. Copper, we are going to get copper solid, then plus some zinc what? Zinc sulfate. Now that chemistry of replacing a less electropositive element, that one is the displacement. So it comes from the definition of displacement reaction here. Now the heat produced, therefore, this one we can say this is the amount of heat produced. So we are saying enthalpy of displacement we are basing on the ability of a more electropositive element replacing a less electropositive element. We are using an example of copper and zinc, copper being lower, zinc being higher. So we see zinc replacing copper. It can even be iron. If, for example, I have iron, take a note of that, iron, and then I'm reacting with a solution of copper to sulfate. Now I've added this iron powder or filings. Of course, we are going to discover that iron being higher is going to replace this, and we shall end up getting iron to sulfate, and copper remains copper solid, like that. So we can define enthalpy of displacement as the amount of heat produced when 1 mole, amount of heat produced when 1 mole of a less electropositive element has been replaced by a more electropositive element. So I have used an example of copper being lower than zinc. So zinc displaces copper, or iron being higher displaces copper. Now how can we determine this one? We are going to use an example of the experiment where we shall now have our, if I'm going now to use some illustration here, there we are going to put copper to sulfate in the beaker, copper to sulfate in the beaker. This one is our copper to sulfate solution. Then what are we going to add? We shall add now some zinc powder, and then we are going to stir with the thermometer. So we have our zinc powder there, and then we have our thermometer. Then what are we going to do? Initially we are going to record the temperature. Of the copper to sulfate. Then afterwards we are going to record the temperature of the mixture as we are stirring. So in simple terms, remember when you are describing an experiment based on your procedure, how many procedure here we are going to put a known volume. A known volume, it means you have measured using a measuring cylinder, known volume of copper to sulfate solution. For you don't write formula in the description, you write your word. A known volume of copper to sulfate is placed in a thick walled tin, or it can even be a beaker. Don't forget that, you can use a beaker. Then afterwards we are going to add a known mass of zinc. It can even be iron, you can even add iron. Then what next? Then we stir the mixture, and we record the what? Record the temperature rise. It can even be temperature what? Temperature change. Simple as that. Then from there we are going to assume that the following are our results. So we are going to assume the following are our results. So we may have our, let us assume that our results are like the following. These ones are our results, which we are going to use for calculating. We are going to assume that the volume of copper 2 sulfate, for instance, that is equivalent. Let us assume that we have used 50 cubic centimeters, the one we measured and placed here. There is something which you have to note here. Copper 2 sulfate is pale blue. So as you are putting the zinc powder, our observation here, before you continue with the results, our observation here, we see that the pale blue solution turns to a colorless what? A colorless solution. Don't forget that. That is an observation which is needed. Then the equation of the reaction, we shall take the other one. Now from there, we are going to assume that this is our volume. Now members, our observation here, we are saying a pale blue solution turns to a colorless what? Solution. Now the colorless solution, that is the zinc sulfate we talked about. Remember, the zinc, we are forming zinc sulfate. Then we are having given, remember our equation is going to be, let me put the equation clearly. What we are saying, you have copper 2 sulfate, then you are adding there zinc solid. That one implies that you have zinc solid, so you have copper solid plus zinc what? Zinc sulfate. Zinc sulfate is colorless, then copper is brown. So the observation we are going to get, this one is pale blue. So our observation here is going to become that the pale blue solution turns to a colorless solution. Then we shall see some brown deposits here. We have some brown what? Brown deposits. The brown deposits are for what? Those brown deposits are for what? For the formed copper here. Then the colorless solution is because of the formed zinc what? Zinc sulfate. So pale blue turns to colorless solution with the brown what? Brown deposits here. They can ask you that observation. Don't forget that. So when you come back to our results here, so we have that volume. Then let us assume that initial temperature of what? Of the solution is equivalent to 25.0 degrees centigrade. Then the final temperature is going to become 28.5 degrees centigrade. Now we are going to find out the heat. The heat of displacement, that is the heat produced, is going to become now our formula which we use, the mass times specific capacity times change in heat or change in temperature. Now from there we shall find our mass. Our mass is where? We are going to get the volume which we used, which was the 50 times the density. So we shall get 50 times 1, the density. Don't forget that we say the mass is equivalent to density times what? Volume. That formula should be in the head. And there, members, we have 50 grams. Then we shall find the change in heat or temperature. So that one we are going to get the final minus the initial. Our final is 28.5, then minus 25. Now the degrees we are going to get there, when you minus, try to use your calculator and you see the degrees there. Here we are going to obtain now the degrees which are, that is 28.5 minus 25, that is 3.5 degrees centigrade. Now after doing that, we are going to substitute. Therefore our heat is going to be equivalent to 50 times the 4.2. 4.2, that is specific heat capacity. This one times now the 3.5. And now our final answer here, we are going to obtain, get a calculator also, and you check what you have here. We have 735 joules, or they can even be kilojoules. And from there, now we are going to find the number of moles which are producing this heat. How are we going to find them? That is by going back to our copper 2 sulfate. What was the molality of copper 2 sulfate? Here we have to specify the molality of copper 2 sulfate. We are going to assume that the molality of copper 2 sulfate maybe it was 0.5 molar. 0.5 molar. The one we used. Let me make it clear, assuming 0.5 molar. The copper 2 sulfate which we used. So here we shall come and say 1,000 cubic centimeters of the solution contain the 0.5 of copper 2 sulfate. Then what about the 50? This 50 here, the volume we use it. About the 50 cubic centimeters of the solution, we are going to cross multiply members. That is 50 times 0.5 out of 1,000. And now we are going to obtain, get your calculator also, we are obtaining 0.025 moles. Then from there, we are going to find the mole ratio. We are going to get mole ratio. Remember our equation is that we have zinc plus copper 2 sulfate, aqueous, and this is solid. And here we are obtaining what we call zinc sulfate, then plus copper solid. Now, our mole ratio here is going to become, because of zinc are going to remain 0.5. So we are having zinc moles now. From mole ratio, they are going to become 0.025. Now, those are the moles which are depositing this amount of heat. So we shall say that is 0.025 moles of zinc deposit now, or produce. Let me use the arrow because of the space. Produce the heat which we calculated, this one, the 735. Remember, as here the mole ratio, I beg your pardon, the mole ratio here, we are considering that one of zinc and that one of copper 2 sulfate. That one of zinc and that one of copper 2 sulfate. Because we want to find the zinc now, moles. So from there, this one produces that amount of joules. Then we are going to say what about the 1 mole? About 1 mole produce now of the zinc produce. So we shall get 1 times 735 out of 0.025. And our final answer here is going to become now 29400 when you get your calculator joules. If you are converting to kilojoules, now we are going to obtain 29.4 kilojoules. Remember, you are dividing with 1,000 to get the kilojoule. Now, this enthalpy is negative enthalpy, so we put a negative. Similarly, with this one of enthalpy of combustion, it was negative somewhere. So meaning, even this one of neutralization, it is also negative here. Don't forget to mean that they are ectothermic. So here we are meaning the reaction is ectothermic reaction.